So this is Math 148, Section 9.9. We finally worked our way all the way through Chapter 9, which is all derivatives all the time. And Section 9.9 is looking at applications of derivatives, so no more strange formulas. Applications. So I'm going to tell you a little bit about these applications in general, and then I'm going to do one problem all the way through for you. So in general, for these applications, they give you a function, and I'm looking at example 1 on page 618. They give you a revenue function. So here's, they say the revenue function is some function where x is the number of products, the number of things sold. If this is your revenue function, then the first derivative of x is called the marginal revenue, and it's written like this, MR. It's the marginal revenue, and this is probably or potentially a new word for many of you. So the marginal revenue, the way you interpret this, there's a beautiful sentence here on the bottom of page 618 that says the marginal revenue is an approximation or estimation of the revenue gained from the sale of one additional unit. So R prime of x approximates, so it's estimating, it's not exact, the increase of revenue, or the revenue, it might be a decrease, gained from the sale of one additional unit. And this is going to be an interpretation you're going to see over and over again. So I'll read that sentence again. The marginal revenue is an approximation or estimation of the revenue gained from the sale of one additional unit. So if you want to say, okay, we sold, what was our revenue for 100? Okay, what's our revenue for 101? Well, you can use this derivative to approximate, it's the rate of change of revenue, so it's the increase. So here's another application. Suppose you have a cost function, okay, and you have some cost, C of x is the cost. You'll notice there's a difference between the revenue and the cost. The revenue is how much money you're bringing in. The cost is how much it costs you to make it. So the cost function, to make X units of things, blenders, printers, whatever, the first derivative of the cost function is, they write it like this, MC. So you can probably imagine this is, yes, it is the marginal cost. So what is the marginal cost? How do you interpret the marginal cost? So if you're given a function, at this point finding the derivative, I bet you can do it. You just use those derivative functions. But how do you interpret the marginal cost? Well, again, they have this nice sentence here. The marginal cost is used to estimate the amount that the total cost would change if the production is increased by 1. So this is a very similar sentence. It estimates the total cost, right? Total cost, how it would change. So it might go up, so you could say how much the cost will increase or how much the cost will decrease when you basically produce one more unit, or when the production increases by 1. Okay, I'll do one more for you. So here's roughly example, looking like example number 5 in your book on page 621. So you could have, yes, P of x is going to be a profit function. So what is your profit when you are producing or selling X units? Most of the time it's when you sell X units, what is your profit? You'll notice revenue is different from cost, which is different from profit. And obviously, profit is equal to revenue minus cost. But you can also talk about the marginal profit, MP. Do you see the pattern here? Marginal profit, MP, with a line on top. And this is calculated by taking the first derivative of the profit function. So if you're given some profit function that asks you to find the marginal, the M is here, marginal profit, then you take the first derivative. And in this case, it's because marginal is rate of change. That's how they're using this word. It is the rate of change of profit. And if you have this derivative for the marginal function and you plug it in at some value, let's say 100, here is how you would interpret this. you would say the marginal profit, let's say you calculate the marginal profit and you plug it into some function at 100 and you get 5. I just made up these numbers, but here's the interpretation. You would say the profit as x goes from 100 to 101, so again the change when you increase one thing, the profit that we would expect from going from the production of x equals 100 to 101 is 5. So in this case we're saying if you're, and again I sort of invented these numbers, but let's say we had some profit function and we said what is this profit function, the derivative, and you take the derivative and you evaluate that at 100 and you get 5, you'd say the additional profit we would expect to make if we made in the change from 100 to selling 101 units would be positive $5. So for all of these application problems, when you see the word marginal, they essentially are saying find the first derivative and then interpret it in this way where you say it's the profit or the revenue or the cost that you would expect from increasing one more at whatever point you're looking at. So I'm going to show you a longer problem that works out a full example of this. 3 on page 624. And question 3 says, suppose that the total revenue function for a commodity is R equals 36 minus 0.01x squared. They don't tell us what commodity, so I like to think of it as orange juice. Why? Because I keep thinking of Trading Places and how they messed up on the commodities market. So, part A says find R of 100 and tell us and say what this represents. So to find R of 100, you basically just plug 100 into there and there. So that's 36 times 100 minus 0.01 times 100. This is a bit of a review from Math 116 or whatever algebra class you took. So that equals 3,500. And what does this represent? Oops, 100, like that. What does this represent? That says the total revenue, how much money you would bring in if you made 100 units. All right, it's probably not orange juice. Maybe it's, I don't know, televisions, but that's not really a commodity. Anyway, if you bring in and sell 100 of them, you made $3,500. Part B says find the marginal revenue function. Okay, well the marginal revenue function, that's the notation, marginal revenue function with this bar on top, and it's the first derivative of the revenue function, which is going to be, I'll use red. This is not the most complicated derivative we have seen. 36 minus, it's 2 times 0.01. I'm just going to jump ahead, multiply that out, 0.02x, because that's 2 times 0.01. So that, right there, is the marginal revenue function. Part C of this question says find the marginal revenue when x equals 100 and tell what it predicts about the sale of the next unit and the next 3 units. So find the marginal revenue at x equals 100. Well, we're going to plug x equals 100 into here. We get 36 minus 0.02 times 100 is equal to $34. Tell us what it predicts. This is what it predicts. It says the additional revenue that we expect, so I'll write out this sentence, the additional revenue that you expect to see from the sale of the 101st unit, from the sale of, because we're already at 100, so if we're going to jump to the next one, so an increase in 1 from 100 is the 101st one, 101st, not 101st San Francisco, first unit is $34. So if you're making 100 things and then you go to the pop-up and you sell one more, you expect to bring in another $34. And for the next 3 units, you expect to make $34 each times 3, so that's going to be $102. So what does it predict about the sale of the next 3 units? It predicts that we will make $102 and increase. Notice that's a positive number. So an increase in revenue of $102 for the next 3 units if you start at 100. So 100, 101, 102, 103. Increase in revenue in 3 units. It's making predictions about how much you think you're going to increase your revenue. And all of these predictions are coming from the fact that derivatives are a rate of change. So how much do you think your revenue is going to change? There's a part D. I need another page. So part D says find R of 101 minus R of 100 and explain what this value represents. Well, let's find R of 101 first and recall, I erased it, but R of x is equal to 36x minus 0.01x squared. So this is the revenue function, not the marginal revenue function. So R of 101 is equal to 3533.99. That's plugging 101 into this equation. And R of 100, if you plug 100 into this, I'll write a few more steps for this one. Sorry if I shortchanged you on the revenue function evaluated at 101. So there was the step in between that I didn't show last time. This is 3,500. Okay, so evaluating R of 101 minus R, the revenue function at 100, this is going to be equal to 3533.99 minus 3,500 is equal to $33.99. So the other part that says explain what this value represents. I notice they're not saying what does this mean, because the mean is another mathematical term and they don't want to confuse you. So they're saying, what does this represent? So I'll tell you what this represents. This represents the actual. This is not estimating anymore. This is the actual change in revenue. So we're saying at 101, we will make, as much as our function is accurate, this much, and at 100 we will bring in this much. So our actual change in revenue when you go from 100 to 101 units sold is 33.99. So the reason they made you do this is they wanted you to appreciate that the marginal revenue predicted that we would make at 100, it predicted $34, and the actual value that you would see is 33.99. So our prediction's really close. So they're trying to get you to really deeply appreciate how accurate these derivative predictions can be in terms of estimating the marginal rates for things. So this section you're going to be doing lots of marginal revenue functions, marginal profit functions, marginal cost functions, and the pattern you're going to use is very much the same like this. You're going to take the derivative, plug in a number, and say this is representing the estimated change that you would expect to see when you increase an additional unit. And I have all the problems worked out on the homework so you can follow along if you're curious about any of them.